classically we have 7 transmembrane receptors, and for some neuropeptides we have maybe 1 transmembrane segment, 1 channel, and for sigma-1 receptors we don't know the endogenous ligand. Steroids, we know that progesterone can act as antagonist on sigma-1 receptors. Neuropeptide Y can also act on sigma-1 receptors. And we know that a lot of antipsychotic, antidepressant, anxiolytic drugs can act on sigma-1 receptors. But still, this receptor is a mystery. Sometimes the prediction said 1 transmembrane receptor. I have seen 7 transmembrane receptor and also 4 transmembrane segments. Okay, so we don't know. It can be addressed at the level of the plasmic membrane, but it can be also present on some organelles like mitochondria, reticulum endoplasmic, reticulum, sorry. So it is not clear. On this slide, where I represent the 2 main aspects of neurotransmission and receptors, you have ionotropic and metabotropic receptors. Ionotropic being characterized by fast transmission, while metabotropic being characterized by lower constant of lower temporality and maybe lower amplitude of effect. So why? For instance, here you have the situation for one of the most famous receptor, which is the NMDA receptor. For glutamate, I think you have all heard about NMDA receptors. Globally excitatory and composed by different subunits. This is a cationic channel. There are sites for agonist, antagonist, allosteric regulation, a lot of drugs, polyamines, etc., etc. So this is fast neurotransmission. And of course, the impact of the cell will be, in first instance, modulation of the membrane potential. Then you have metabotropic receptors, in which here this is related to the activity of G proteins with the alpha subunits of G proteins capable of modulating other intracellular signaling pathways, I don't know, channels, enzymes, protein kinase, protein phosphatase channels, etc., etc. So this is the circuits of G proteins. Be aware that 7 transmembrane receptors can also couple proteins other than G proteins, for instance, beta-arrestin, independently of G proteins. So it is a life of the receptor and the G protein. And of course, the constant of time are longer, and perhaps the effect have to be understood differently. So an action on the cell, plasticity, etc., etc., with long term. So we progress, and I will speak about here one of the main points also proposed by Eccles, the inactivation. And looking at the triggers used by living to destroy the neurotransmitter, I think this is an important point. So, for classical neurotransmitters, you have transporters and degrading enzymes. You have transporters that are specific for serotonin, dopamine, noradrenaline. These are presynaptic plasmalaminal transporters, so they are expressed by the presynaptic element and specific for one of these amines. For instance, a serotonergic cells will express the serotonin transporter, CERT. Dopaminergic cells will express the dopamine transporter, DAT. And noradrenergic cells will express the norepinephrine transporter, NET. You have also transporters for glutamate and GABA. Those transporters are multiple. I think for glutamate, they are called excitatory amino acid transporter. Excitatory amino acid transporter, yes, EAAT, 1, 2, 3, or 4. And there are also other channels or emit channels that are capable of releasing or taking glutamate. And for GABA, I think we have GAT1 to GAT4. These transporters are not necessarily expressed by GABAergic neurons or glutamatergic neurons. Some of them are specific of glial cells. So this is quite complicated now, and we will see that glial cells cannot be dissociated from glutamate and GABA functioning. We have also some degrading enzymes. I mean, for dopamine and noradrenaline, we have the COMT, which is mostly intracellular, but not expressed by monoaminergic cells, expressed by GABAergic cells and maybe glial cells. I don't know, but still, this enzyme is responsible for the methylation of dopamine and noradrenaline degradation. We have also monoamine oxidase, A and B, which is intracellular, which is expressed by cells and which goes on the external membrane of the mitochondria. Then we have acetylcholinesterase. Acetylcholinesterase is synthesized by different types of neuron and eventually released in the synaptic cleft or anchored in in plasmic membrane, so that the catalytic site is inside the synaptic cleft. And at the end, we have histamine. Histamine is a little bit different. We don't know specific transporters for histamine. And as far as I know, it does not cross the biological membrane. So it has to be some sort of transporter. And these are